In this video, we're going to be talking about how to draw and label a heating and cooling curve for any substance. We are going to focus specifically on water, but it can be applied to anything. Couple vocabulary words that we need to review or teach depending on what point in the year we're in and the order that this is taught in, but the individual phase changes. So now we know some of these words. We know when a solid like ice turns into a liquid, we call it melting. The scientific word is fusion. When a liquid turns into a solid, like water turning into ice, we call it freezing. The scientific word is solidification. When a liquid turns into a gas, we would normally call it boiling. The scientific word is vaporization. And when a gas turns back into a liquid, we would call that condensation. We actually use the scientific word for that. Like, for example, when you take a shower and you see the water starts to condense onto the mirror or glass around it, some people would call it fog, but the proper word is condensation. There are two others. Turns out you can, under special circumstances, skip the liquid phase in both directions. So a solid can turn directly into a gas, or a gas can turn directly into a solid. The words are, for a solid jumping to the gas phase, we call it sublimation. And when a gas turns back into a solid, skipping the liquid phase, we call it deposition. So you've definitely seen some of these. Deposition, the most common naturally occurring form of deposition would be frost. So in the fall, when it starts to get cold out at night and you walk out and you see essentially ice on the leaves, that was deposition. It didn't actually, on nights when it frosts, if you pay attention, you'll notice it doesn't rain that night. So the water had to come from somewhere, right? The water, a lot of people would think that the water might come from the grass blade or the plant itself. It turns out it doesn't. It comes from the air. And so the water is in the gas phase, and if the conditions are right, it will crystallize onto the blades of grass, and you see them in the morning as ice. They look like almost little snowflakes. And so that is deposition. Sublimation in the nature, I don't really know of any examples. There are some things that do sublimation, mainly dry ice, if you've ever seen that, or iodine, they can sublime, but we'll talk more about those in a different lesson. Some more vocab words. Entropy is disorder. So when we think about our three phases and you look at the three diagrams, which diagram is the most organized? Well, that would be the solid. So the solid would be the lowest entropy, because remember, entropy is disorder. And then the reverse, the gas, would be the most disorganized, and therefore it would have the highest entropy. Exo and endothermic, and then we can actually start labeling our graphs. So if we break the word up, exo and endo you've heard of in biology. If you think about an exoskeleton or an endoskeleton, we have endoskeletons because our skeletons are on the inside, and bugs have exoskeletons because their skeletons are on the outside. Well, the same use of the word is here, except now instead of skeleton, we're adding the word thermic, which refers to heat. So exothermic means heat is exiting the system. When you think of it, think of exo for exit, and then endo would be entering. So exo, exit is a little bit easier to remember. So for exothermic, heat is exiting the system, and for endothermic, heat is entering the system. All right, so those are exo and endothermic definitions. And then our next two, we just need to go over what chemical reactions look like. So the first thing you have to recognize is that chemical reactions are always separated by an arrow. So my arrow is right here. Everything on the left of the arrow is what we start with. It's what goes into the chemical reaction. We call it the reactants. Everything on the right side of the arrow is what we end with. It's what comes out. We call it a product. So when we think about reactants and products, these two chemical reactions are the chemistry way of saying something very simple. This one on the left is basically saying ice is melting, but it doesn't. When you look at it, it's obviously not as obvious. So this is H2O and this is H2O. The difference is this S means it's in the solid phase, so that's ice. This L means it's in the liquid phase, so that we call that water. And if you look, the energy or the heat is on the left side of the arrow, so it's going into the reaction. So what this is saying is if I take a block of ice and I add a specific amount of heat, I get liquid water. That's a very fancy way of saying you're melting an ice cube. The reverse is also true. If I take liquid water and I can turn it into solid water by removing the heat. Okay, so it's worded a little differently, but this is how we unfortunately have to read them. So liquid water turns into solid water if you pull out the heat that made it a liquid. So it's basically the reverse of that. And then the last thing we have to do before we draw our heating cooling curves is talk about kinetic and potential energies. So heating cooling curves look like this. They kind of look like steps going up and down. Don't worry about why they're different lengths. We'll get into that at like why this platform is shorter than this platform. We can get into that a little bit later. But here's the way to remember kinetic and potential. It's very simple. Kinetic energy, otherwise known as average kinetic energy, or AKE, is the temperature. So if we look at this graph, temperature is on the y, that means temperature is changing on the angle parts and it's staying the same on the flat parts. So if we're reading this from left to right, then the kinetic or the temperature goes up on these three angles and it goes down on the same three if we're looking at a cooling curve. Okay, so that's kinetic energy. Now the thing to remember is that when one form of energy is changing, the other remains constant. So if we think of it here, on the flat parts, the kinetic or the temperature is not changing, that's why it's flat. So therefore, if the kinetic is staying the same and we're still going to the right, then the potential must be increasing. And then the reverse is true here. So when kinetic is going up, potential is not. And when kinetic is staying constant, potential is increasing as we go left to right, or all decreasing as we go left to right for cooling. Now, what's the difference between kinetic and potential? Well, kinetic is obviously heat or the motion energy, whereas potential obviously is potential energy. Now, chemical potential is a little bit harder to explain. Everyone understands, like, for example, if someone was doing construction and they have this big heavy beam and they're lifting it up with a crane, you don't walk under it because obviously if it falls, it will crush you. That's physical potential energy. Chemical potential is a little bit less obvious. It has to do with the molecules and how far apart they are and what they're doing. And so we're just going to learn it as kinetic versus potential, and we're going to really define it as a kinetic or not kinetic. But potential is there. It is a little bit more complicated. We can explain it more if you need more than that at a later date. In this video, we're going to be drawing heating and cooling curves for water, but these curves can apply to anything. So the heating cooling curves, they look like a series of steps. We've got the steps going up and we've got the steps going down. The ones going up would be called the heating curve because as time goes on it gets hotter, and the reverse is true for the cooling curve. We've got temperature on the y, time on the x. The time itself doesn't really matter for this curve because we're just doing a basic drawing. It's really just about identifying the different parts. When you do this in a lab or things like that, then the time may matter. You know, there may be increments on the time, but I'm really keeping the increments. For the most part, we're not going to write any of them in, because we're just working on identifying stuff. So the first things that I like to label when doing these are going to be the flat parts. All right, so now if we think about what's going on, for the heating curve, we have the first flat part is going to represent the melting point, and then the second one would be the boiling point. Now, boiling point, you could technically also call it the condensation point, and the melting point can also be called the freezing point. But most people just call it boiling point and melting point. It's just easier. And for water, it would be specifically 100C and 0C. Now, that's water, obviously. This curve can be applied to anything. So one thing to keep in mind is if it's not 0 and 100, then it's not water. Those are the main melting points for pure water. Obviously, we can change those melting points if we're not dealing with pure water, but for pure water, it's 0 and 100. And then for here, it would be the same thing. This would be 100. This would be 0. All right, and so those are our boiling points and melting points. Now the next part is going to be the phases. Those are the next easiest thing to label. So when water is below freezing, it would be a solid. So this would be my solid water. And if I were to do a phase diagram, it would be a repeating geometric pattern. You could fill the whole thing or not, it doesn't matter. So there's my phase diagram. Above the melting point, the water would have melted, and so therefore it would be turned into a liquid. So there's my liquid. Now for the liquid, I just randomly put a bunch of Circles will represent my water molecules, and I like to only fill the box about halfway. And we try to keep them relatively close together. If you filled it the whole way, it wouldn't necessarily be wrong as long as it's not in a repeating pattern. And then when you're above the boiling point, you're a gas. So those, I spread them out. I don't use as many. I fill the whole container because gas particles are really far apart. That's how you just, and they're totally random, but the real difference between the liquid and the gas is the distance between the particles, and the gases will always fill the whole container, whereas the liquids, if it's only half filled, then they only fill half the container. All right, so there's solid, liquid, gas. Now we would also do the same on the reverse. So we've got gas, liquid, solid, and our phase diagrams would be the same thing. Randomized, fill the whole container. Closer together, but also randomized. I only fill half the container. Repeating, geometric. Sometimes they use the word geocentric, but the same idea. Repeating geometric pattern for the solid. So there's my solid, liquid, gases. Next part, let's talk about the phase changes. So we know those. When a solid turns into a liquid, so in other words, if we're going in this direction, we would call that melting. The scientific word is fusion. All right, the reverse of fusion is freezing or solidification, so we don't even have to think about it. Once we identify fusion, we know the other side is solidification, and we can do this here too. Now, there's two ways of doing it. Some people like to keep the arrows in the same direction, the top and the bottom, but you could also flip them, it doesn't matter, so I'll show you both ways. If a liquid turns into a solid, so if we're going in this direction, this would be solidification, and then the reverse is fusion. Now, I don't care how you label it, meaning if I put the fusion on top, the arrow would just have to be pointing to the left here, and if I kept solidification on bottom, the arrow would still have to go to the right. So as long as the arrow matches up with the proper word that's describing the phase change, then it doesn't matter which one you put on top or bottom. But also the nice thing is, as long as you know one, like if you just know fusion is melting, therefore solidification, you can just flip it. It's not hard to memorize them both, but it's one less thing you have to memorize. Now for boiling is when a liquid turns into a gas. So vaporization, same thing here. It would be, I'll flip it just to show that it doesn't matter. So there's vaporization. So if you notice, I kept it on top both times in this example. I just changed the arrow, so that's totally fine. As long as you have the word in the arrow that matches, it doesn't really matter. And then the reverse, condensation. So those are pretty easy. That's most of a heating cooling curve. And then the last things we have to worry about, I guess I'll switch. I don't really need to switch color on these, but we're going to talk about the firsts and the lasts. So the firsts and the lasts show up on the corners, right? So I'm just gonna, you don't have to put a dot here. I'm putting a dot to make it more obvious what I'm talking about. So we have what happens there, first there, there, and there. So the corners. So now if you think about what's happening, right here, we have a solid block of ice. Its temperature is in the negative Celsius at some degree. I don't care how negative it goes. But as it's warming up, when it initially hits 0 degrees, that's when melting begins. So visibly, what you would see is the first appearance of a liquid. So we would say that at this corner is when the first liquid shows up. Then, now, when we're on this flat part, the ice cube is getting smaller and smaller, and the amount of liquid water is increasing, and so the ice cube gets smaller and smaller and smaller until at this very last corner is when the last piece of ice disappears. So that's when your ice cube formally, officially, fully disappears from view. You can't see it anymore. That's that corner. And then the next corner, again, now we have liquid water, and we're heating it up. When it gets to 100, it begins to boil. That's when we see our first air bubbles, usually at the bottom. Well, not air, but first gas bubbles. They're usually at the bottom of the pan if we're boiling water, things like that. And now, if we're boiling the water on this flat part, the water is evaporating into the air or vaporizing into the air, and you're going to have less and less water. Eventually, all the water is going to be gone. So this is when your last little drop of water finally vaporizes into a gas. So there's your firsts and lasts. Now, if that was hard, watch, there's a much easier way of remembering it. So hopefully this makes it a little bit easier. I like to do it. It's always the way we read, left to right. First, last. They always go first, last, first, last. So if you notice, on this side, it did the same thing. First, last, left to right, the way we read. And for cooling, it does the same thing. First, last, first, last. So that gets rid of that. You don't even, that part of it, you don't even have to memorize. You just know it goes first, last, and the whole thing is done. And then the question is first what and last what. It's always the phase on the opposite side. So in other words, on this side, I'm on the gas phase. Like this is gas, I'm on the side of the gas. So this would be the first appearance of liquid, because liquid's on the opposite side. Now I'm on the liquid side, so the opposite would be the gas. So this is last gas. This one would be first solid, because the opposite side is solid, and this would be last liquid, because now I'm on the solid and the opposite side is liquid. You can also talk your way through it. If you think about it, you have a really hot gas here. It's starting to cool down. Eventually it will start to condense. That's the flat part. It will start to condense, and the way we know that it's starting to condense is we will see our first drops of liquid appear, like on the glass or on the container or whatever. We'll see some liquid show up. That's why it's first liquid. Now the gas is condensing, so we're going to have less and less gas and more liquid. Eventually it will finish condensing, and that's where the last bit of gas turns into a liquid. That's obviously invisible to us, but you can imagine it in your mind. That's what's happening. And now we have a total liquid, right? And so the liquid's going to get colder and colder. Eventually it's going to hit zero and begin to freeze. That's where we see our first pieces of solid ice showing up. And now as we are doing this, the liquid is becoming more and more solid, and it's becoming more solid, more ice, less liquid in this case. And eventually it'll be done freezing. That's this other flat part. And therefore the last bit of liquid will disappear. So that's pretty much a heating cooling curve. There are two more things we have to know, and then we're done. So I'm going to draw them like this and like that. So basically the endo and exothermic directions. There's a saying. I want you to write it down. When you exit a building, you go downstairs. Now, obviously, it's not always true. If you're in the basement, you're going to go upstairs, but it's a generalization, and it's really just a device for remembering which direction is exothermic. So if you think about it, exo and exit, they both have the EX in it, so therefore the exit direction is always down the stairs. So if we think about the down, if we're talking about the heating curve, down would actually be to the left, so this is the exothermic direction. And if we think about a cooling curve, the down would be to the right. So that's the exothermic direction. It's always down the stairs, and whichever way happens to be down. And then the reverse is exothermic, or endothermic, sorry. So that is a fully labeled heating and cooling curve. At some point you will eventually get a quiz on this. The quiz will effectively be a blank one. The only thing you will get is the sketch of the curve, and then I will put in, instead of, S, fusion and solidification, and L, I'll put in, number 1, number 2, number 3, number 4, and all the firsts and lasts and all of it, and you'll have to label and tell me what everything is on your own. I do want the scientific words, not the common words. So I don't want to see melting and freezing. I want fusion and solidification. I don't care if you call it melting point or freezing point or boiling point or condensation point. They mean the same thing because they happen at the same temperature. They're just reversed directions, meaning melting is when a solid turns into a liquid, and freezing is when a liquid turns back into a solid, but that's essentially the same thing. It's just energy going in or out. So that is the fully drawn heating cooling curve.